All right, folks, this is where we're working with RLC series circuit. I've chosen RLC so I can include both capacitor and inductor in one demonstration. Of course, if you're doing just RC or RL, then you would just have two components instead of three like I have shown here in series. So I'm just going to review the circuit connections before we look at using the instrument. So if you look here, you can see that I have the power supply connections from my AC source, of course, and this is our source, of which we said you should always connect to neutral and to terminal number 5. This is going to give you a phase to neutral voltage or an AC voltage as your source voltage in your circuit. So that comes from our AC supply, and we familiarized you with the setup of it last class. So you can see I've got that connection. Now I'm going to set up a series RLC circuit. So just as if we had a DC circuit, I'm going to follow this conductor from the source to my first component. And you can see the first component I've chose is a resistance of 100 ohms. So I've got the connection there. Now the current flows through that resistance and exits on this blue wire and goes to the inductor. And you can see that I've chosen a 300 millihenry inductor for my second load in my series circuit. Then the current carries on with a single path for current to flow to my exiting my inductor, and now with the yellow wire the current is entering the capacitor, and in this case I chose the 33 microfarad, and now the current exits the capacitor and returns to the source, and it returns to the neutral or the white lead. So I told you for all circuits going forward, what you're going to do is to connect to 5 and neutral. And therefore, when you set this up here, 5 to N, that means that the analog meter is going to be showing the a rough value of the voltage, or a estimate of the voltage that's on the terminals. Now, of course, you want to use a proper instrument to measure that voltage, but this is going to show you a rough value. Now, you can see right now I've got 0 volts AC applied. So you can see as I'm turning the knob here, so I'm just turning the knob, and you can see that value going up. And I'm shooting for 50 volts AC here. So I'm going to put it there, and then I'm going to connect my power analyzer and the voltmeter leads of the power analyzer to measure that voltage, right? So now if I look up here and I look at the voltage that I've got represented for my power analyzer, I'm a little bit too high, right? So I'm just going to drop that down to give me 50 volts of applied power, right? So now I have voltage of 50 volts AC. Okay, so that's the way you properly set that value from the source. Okay, so now when I look at this circuit, I have a series circuit which is going to be a voltage divider. So that means that I can look at the voltage of the resistor, the voltage of the inductor, and the voltage of the capacitor, and as long as I'm adding them up at their appropriate angles, then I can prove Kirchhoff's voltage law for this circuit, where all the voltages add up to the source voltage of 50 volts. Okay, so let's take a look at that next. Okay, so you can see what I've done next here. I've connected the power analyzer to measure the voltage of the resistor. Okay, so now when I look at my power analyzer and the voltage, what I'm seeing here is the sine wave and the RMS value of that resistor voltage, and in this case that's 46.6 volts. Okay, so just like any other voltmeter, if you want to determine the voltage of the inductor now, you would just move the voltmeter to being across the inductor and look at your voltmeter, and you can see we have 50 volts. Now remember, we only have 50 volts in total here. So why is it that we can have two voltages of near 50 volts and they add up to being only 50 volts? Remember, it has to do with these reactive voltages, right? So now let's move to the capacitor voltage. If I move to the capacitor voltage, notice how we have 37 volts. So what we need to do is understand the angular relationship between the voltages we just read. First of all, we had the resistor voltage. That's at 0 degrees. Then we have the inductor voltage. That's at plus 90 degrees. VL is at plus 90 degrees. Then we have the capacitor voltage. That's at minus 90 degrees. VC is at minus 90 degrees. So what it means is we have this voltage and this voltage that are 180 degrees out of phase, so they counteract each other. So what you're going to have is the net reactive voltage left over, of which needs to be added to your resistor voltage in order to verify your source voltage of 50 volts. So if we go down here and we connect back to our source voltage, all of those voltages when added together would equal 50 volts AC RMS. Okay, let's take a look at the current measurement then. And let's understand that obviously in a series circuit, it doesn't matter where we connect the probe, it'll be the same current. So for a series circuit, we know that IR will equal IL will equal IC. So if I just measure the conductor and the current in the conductor that connects to this series circuit, I'll have the same current for all three components. So that's what I'm going to set up next here. So you can see I've set up the current clamp here for this series circuit to measure the total current. And we know that I total equals IR equals IL equals IC. So when we look at the power analyzer here, we can see that we have 457 milliamps of current in this circuit. And this is all going to be determined by the total impedance divided into the applied voltage. So we can verify that by using our impedance and our calculation for series impedance to verify that. Notice how I've set up the arrow on the current clamp corresponding to the same polarity of which the voltmeter part of the power analyzer is set. Notice how I have the red lead of the power analyzer on the red connection and the black lead on the black connection. Therefore, if we were to look at the voltmeter providing that reference for polarity, we would have current in this direction, right? Now we know we have current alternating in an AC circuit, but in terms of using the power analyzer, we've got to make sure that that arrow is consistent with the polarity that's been set by the voltmeter. So you can see that we would have to set that up in that direction. Now for the current measurement itself, that doesn't matter, but where it matters is when we look at the power menu. Okay, so that's what I'm going to do is I'm going to go to our power analyzer and I'm going to move to the power menu now. And when I move to the power menu, notice how we have a value of watts and a value of VAs and a value of VARs. So what does that mean in terms of power? Well, watts is what you know as real work producing power. It can be translated to BTU or horsepower, and it's real work being done. When it comes to our imaginary power, which comes from your inductor in this case, and notice how it identifies it as an inductor with that coil symbol there, it's indicating that our imaginary power, which is a unit called VARs, which stands for volts amps reactive, is the combination of multiplying reactive volts times reactive amps to give us something called VARs. Now notice how we have primarily inductive VARs here, and if we go back to our voltages, if you remember, our inductor had a larger voltage than our capacitor. Our inductor had about a 50 volt voltage, and our capacitor had about a 37 volt voltage. That means that with a primarily inductive voltage, that's going to be a primarily inductive power, because the current is all the same. So that being the case, you can see the power is indicating that. Now, what is the total power then? What is the total of all real power added to the total reactive power? That's something called VAs. So you can see we have 23.1 VAs here. Okay. Now, the next thing we can do is I can illustrate how we can determine the phase angle from this circuit. So next thing I'm going to do is I'm going to go to the menu, and I'm going to go down to scope, the oscilloscope, and hit enter. Once I hit oscilloscope and enter, you can see how it's showing the voltage waveform as a sine wave, and it gives us the value of 50.5 volts. Okay. Now, what I'm going to do is I'm going to go to setup. Now, if I look at setup, you can see that I have, for input 1, I have my AC plus DC RMS. So that's what I'm getting as far as my, that's what I'm getting as far as my voltage goes on channel 1. But I want to show you something. If I go reading and you look at all the options here, notice how you don't see phase angle in there. Now, there's a reason why you don't see phase angle in there, and that's because when it comes to the power analyzer, it is going forward with the assumption that your voltage will be your reference. So your voltage will be your reference. So if I scroll down to input 2, notice how at the very bottom on the left-hand side, we see another option called phase. So what it means is that phase can only be set for the current. The power analyzer will only give you a result for phase angle with voltage as the reference. Okay, so it will always choose voltage as the reference, and it's only a setting you can do for your channel 2 or your current clamp. So watch what happens here. I'm going to hit enter. Now you can see it changed to phase. I'm going to hit enter, and then I'm going to go back to my oscilloscope display, and notice how now we see two waveforms. And notice how they're marked. Notice how the smaller one is marked with a number 1, and the larger waveform is marked with a number 2. That's saying that number 2 is our current and number 1 is our voltage. Notice how they're not much displaced as far as phase angle goes, but we can see that we have a minus 15 degree phase angle resulting from a primarily inductive circuit. And we know that when it comes to the acronym ELI, it's telling us that for a primarily inductive circuit, the current will be lagging the voltage, and a negative degree for phase angle is giving us exactly that, a lagging current. So a minus 13 degree phase angle. So that's how you use the power analyzer to determine phase angle.